Hello guys, welcome to my channel again. So today we are going to work on the continuation of the existing interview series. So this is the part 2 series of the previous one. So in the previous video we took a look at multi-threading and concurrency. Now in this video we are going to take a look at Java memory management, which we also call as JMM. So in this video we are going to work on all those questions which could be asked in your interview related to this topic. So if you haven't yet subscribed to my channel yet, please do, because I am going to post a lot of videos like this. So keep looking at the videos, subscribe to my channel and share if you want to. Now let's not waste any more time and take a look at the questions. Alright, so the first question is explain the difference between young generation, old generation and metaspace in JVM memory. So young generation and old generation were already there before Java 8, and metaspace was introduced in Java 8. So metaspace was introduced in Java 8 to replace the perm_gen, which was permanent generation, and it stores metadata, as the name suggests, about the classes loaded by the JVM. Now the young generation purpose is to store short-lived objects. Old generation is for long-lived objects, and metaspace stores class metadata. Now young generation and old generation are part of heap, but metaspace is native memory, which is outside the heap. Now in young generation and old generation we have garbage collection. So in young generation we have minor GC, which is a lot frequent and fast, but in old generation we have major GC, which is infrequent and slow. But metaspace is managed as part of class unloading. So I hope the difference is clear now. So in young generation we have add-in space, we have survivor space. So add-in space is the region where all new objects are initially allocated, and survivor spaces are S0 and S1. So after the garbage collection, after the first garbage collection, surviving objects are moved to one of the survivor spaces. Okay, the survivor spaces alternate roles between sender and receiver during subsequent collections. Now old generation is a promotion from young generation. So objects that survive several minor GCs in the young generation are eventually moved to old generation. And in old generation we have less frequent garbage collection, and this generation is typically larger and is used for objects that are expected to remain alive for a long time. Now the next question, how does garbage collection work in Java? Explain G1 GC and when it is preferred. So garbage collection is a very vast concept, but as we have talked about, it is an automated process which basically manages memory by reclaiming unused object. So this is to prevent memory leaks and ensure that there is an efficient memory utilization. So the garbage collection happens only on heap memory. Okay, now how does it work? So when a Java program creates an object, so we have a new object in the heap memory. Now let's say that if that object is no longer being used by any portion of the program, then in that case it is an unused object, and this makes it eligible for garbage collection. Now we have mark and sweep algorithm, which is a general garbage collection process. So we have two phases here. One is mark phase, another one is sweep phase. So in mark phase, the garbage collector identifies all reachable objects by starting from the root reference. Okay, so it could be anything. It could be a local variable, it could be a static variable, or let's say a thread stack. Now in sweep phase, unreachable objects are removed and their memory is reclaimed. So this is your general GC process. Now we have generational garbage collection. So we talked about young generation, old generation. So as we already know that new objects are allocated in the young generation and surviving objects are promoted to old generation. Right, now we have different types of garbage collection. We have minor GC, we have major GC. So minor GC focuses on young generation, major GC focuses on old generation. Then we have class unloading, which removes metadata for classes that are no longer used. Now there are certain algorithm, like we talked about mark and sweep algorithm. We have serial GC, we have parallel GC, we have CMS, we have G1, and then we have ZGC. So let's talk about that in a brief. So single GC is single threaded garbage collection, which is suitable for single threaded or low latency application, right? So this is as simple as it is. Now we have parallel GC, which means multiple threads, and this is optimized for multi-threaded application. That's it. Now CMS is very important. So CMS is concurrent mark sweep. So we already talked about mark sweep. Now this is concurrent mark sweep. So this reduces stop the word pauses. So stop the word is basically a terminology which means everything stops within your application. So this reduces those pauses and it performs most of its work concurrently with the application. That is why we say concurrent. Now we have G1 GC, which we need to explain. So G1 means garbage first. It is going to split the heap into several regions, and then it prioritizes regions with the most garbage first. So what happens is whatever portion of the heap has the most eligible garbage, most eligible objects for garbage collection, that portion of the heap is going to be garbage collected first, right? Now we have ZGC, which is a low latency garbage collector suitable for applications requiring minimal pause time. Now the next question, explain the structure of JVM memory. What are the roles of heap, stack, metaspace and code cache? So we have talked about it. So heap basically contains your young generation, old generation, right? And metaspace is a separate portion outside heap. So it stores metadata about classes. This is located in native memory. Alright. Now stack memory is method specific data such as your local variables, method call information. So basically your call stack and your primitive data types. So these information is going to be in your stack. Now we have threads. So each thread has its own stack, and so stack is a data structure. We know that it operates in a last in first out manner, and that is going to be there. Now we have PC register. So this is a program counter, and this tracks the address of the next instruction to execute in a thread. So this is thread specific, which means each thread has its own PC register. So it's part of your stack. Then you have native method stack, which stores native method calls and their context. That's it. Now talking about code cache, this is to store the compiled native code generated by the JIT compiler, which is just-in-time compiler. So it improves execution speed by avoiding repetitive interpretation of frequently used code, and it stores optimized machine code for methods that are invoked frequently. So anytime someone asks you about JIT compiler, don't forget code cache. This is a must, and vice versa, right? Let's move on to the next question. How can you monitor and troubleshoot memory leaks in Java application? So there is no easy way to debug a big application. You have some tools which you can use. So you have JVM monitoring tools, and you have some third-party tools. So JVM monitoring tools, we have like JVisual VM, we have JConsole that you can use. Third-party tools like Eclipse Memory Analyzer is there, Visual VM is there, and we have YoKit. So a lot of applications to identify memory leaks. Or what you can do is you need to find out the symptoms of memory leaks. So let's say that if heap uses continues to increase over time, track that, because if it is going to increase over time, then in near future it is going to completely use your heap area. Now track your out of memory error. So this the application eventually crashes with this error. Your long GC pauses, which is basically going to indicate that there is an excessive effort by GC to reclaim memory. Now the most accurate way that I know of is to debug memory leaks. And how to do that? You can generate a heap dump when the application is running with high memory usage. So you can use JMap or JVisual VM, anything. Then analyze the heap dump using Visual VM or Eclipse Mat. So then you need to see in the heap dump that what are the objects with high retention size. Look for the suspected GC roots, which are your static variables holding references. Also investigate reference chains to understand why an object is not garbage collected. So again, there is no easy way. You have to look deep. You have to analyze the heap dump, and if you get to know about the source of that leak, you have to fix the memory leak, like static collectors retaining references to unused object, right? So static variable could be one of the problem. Your event listeners or callbacks, your thread local variables, or let's say if you have used caching, then unbounded or poorly managed caches could be the issue. Now there are some best practices to fix leak, like you can use weak hash map for caches where keys should not prevent garbage collection. Explicitly deregister listeners or callback. Use thread local.remove to clear variables, and implement proper cache eviction policies, right? Now there are some libraries like Java profile tools. I already told you about Yorkit. Then there is JProfiler. So this detects leak during development and testing, so you can use that. And also you can write stress test, like you can use JMeter to simulate long running processes and observe memory behavior. So yeah, this is a very big topic to discuss on, but yeah, there is no easy way. Now what are memory leaks if you don't know about, and since Java has automatic garbage collection, how can memory leaks still occur? So garbage collection is not perfect. You have to understand that it is an automated process, but it doesn't mean that it is going to happen immediately. So nothing happens immediately. Let's say that if an object is eligible for garbage collection, it doesn't mean that the garbage collector will run and free the memory. Leak. So memory leak is when an application unintentionally retains references to objects that are no longer needed. So this prevents garbage collection from reclaim their memory. As a result, the application consumes more memory over time, which can eventually lead to performance degradation. So this is your memory leak. Now how would you identify and debug a memory leak in Java application? We have already talked about it. Now what is the role of soft references, weak references, phantom references in managing memory? So we have just talked about weak hash map, and that was the key in terms of managing memory. Now let's talk about soft references and phantom references as well. So references is basically towards your memory, so it is just a reference. Now we have strong reference, which is like let's say string s equals to new string, right? So this is a strong reference. So this prevents garbage collection as long as the reference exists. That's it. So if I do string s equals to null, then it is going to be eligible. Otherwise this is a reference. So this is an example of strong reference. Now soft reference is to retain object that may be cleared if memory is low, providing a cache-like behavior. So how do we do that? So let's take an example. So let's say if you have string data equals to new string soft reference, right? So now here you will create a soft reference of that object data. Now when you do data equals to null, which means that you have removed your strong reference, but it doesn't mean that garbage collection will happen immediately. So what soft reference will do, it will check if the object is still available. So here if you see, we have softref.get not equals to null. So if it is not equals to null, which means that object is still available. Else we have garbage collected that object. So this is suitable for implementing memory sensitive caches. Now weak reference is to hold reference to objects that should be garbage collected when no strong reference exists. So common example is your weak hash map, where entries are removed automatically when keys are no longer strongly referenced. Now let's take an example. So let's say that we have a weak hash map of type object string. Now here we have one object with key 1, another object with key 2. Now we have inserted both of these entries. with value 1 and value 2. Now let's say if we do key 1 equals to null, in that case what will happen is so there is no strong reference for the entry, for the first entry, right? So if I request garbage collection, so remember that this doesn't mean that this will happen immediately. Okay, so so here I have put a timer to wait for 1 second basically, and if you print that hash map now, you will see that the first entry is not there anymore, so the output is going to be just your entry 2. Now talking about phantom reference, phantom reference is basically used to track objects that are about to be finalized and garbage collected. So unlike soft and weak reference, a phantom reference get method always return null. So it requires a reference queue which receives notification when the object is finalized, and this is used for post GC cleanup or resource management task. Now to summarize, purpose of weak reference is to refer to object that should be garbage collected if no strong reference exists. For soft reference, it holds object that can be garbage collected only if JVM is low on memory. Phantom reference tracks objects that are about to be finalized but not yet reclaimed. Now the garbage collection here for weak reference cleared during the next GC cycle if no strong reference exists. For soft reference, it is cleared only if JVM is running low on memory. For phantom reference, it is cleared after finalization before GC reclaims memory. Alright, now let's move on to the next question. What happens if a thread allocates more stack memory than available? So the answer is stack overflow error, and that's why the second question is explains stack overflow error. Now this is very simple. So if let's say a thread allocates more memory, what will happen? This is an overflow, right? So this is pretty much understandable. So definition wise, this will only happen when the call stack, which is the region of memory that stores method calls and local variables, exceeds its allowed limit, right? So this is the definition, but here we are talking about thread. So thread can also cause the overflow because thread also uses stack memory. Now common causes, so let's say if we have infinite recursion or we have deep recursion, so this can happen. Now how to avoid it? So never use infinite recursion, so you have to fix it. So prevent infinite loop, ensure that the recursive method have a base case to terminate the recursion, right? For the recursive depth, you need to limit it. So consider using an iterative approach instead of recursion for tasks that can be represented in a loop. So this was it for this video. I really hope that you found something useful here. So if you did, then don't forget to like, share and subscribe, and stay tuned for more. So thanks so much for watching this video. In the next video, we are going to take a look at exception handling. So stay tuned for that next week, and happy learning. Bye bye.